Hello and welcome to this lesson for OCR A-Level Physics for Module 5, the Newtonian World and Astrophysics, in the concept of gravitational fields and looking at the idea of gravitational fields themselves. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification. So we're going to be looking at 5.4.1 point and spherical masses. Now, a force field is an important concept to understand in physics, as a field is a region in the universe where an object placed inside of it can experience a non-contact force due to its position in the field. Now, the properties of the field are given by the virtual particles of the force interaction, but on the macro scale we can say that objects must contain a certain property to experience a non-contact force when placed inside the field. Now, in gravitational fields, this property is mass. So if we look at the properties of gravitational fields, we can say the following. They act on objects with mass. The fields extend to infinity, they exert weak forces, and these forces are always attractive. Now, any field in physics can be described with four main properties. The definitions of these properties is consistent among all fields. Now, learning these definitions is integral to understanding the physics of any field. So any field in physics can be described with four main properties: the law to calculate the force exerted in the field strength, the potential, and the potential difference. So the first property is the force law, and this details the force exerted between two objects when inside the field, and this is usually named after a famous scientist who's worked in this area of physics. The second property is field strength, and this details the force exerted on an object per unit property of the field due to that object being in the field, and this is down to the force the field produced. So, for example, our gravitational field strength is the force per unit mass experienced by an object inside a gravitational field. The third property is the potential, and this details the energy stored in an object per unit property of the field due to the object being in the field. Now again, this is once again due to the field being produced. So for example, gravitational potential is the gravitational potential energy stored per unit mass in an object inside a gravitational field. Now the fourth property is our potential difference. So this details the work done moving an object per unit property of the field from one point in the field to another point in the field. So the gravitational potential difference is the work done per unit mass experienced by an object moving from one point in the field to another point in the field. Now this is slightly different to the absolute potential difference, which details the work done moving an object per unit property of the field from outside the field, which we define as infinity, to a point in the field. So for example, the absolute gravitational potential difference is the work done per unit mass experienced by an object moving from outside the field to a point in the field. Now we can say that all forces between objects are either contact forces, which are forces produced when objects are physically touching. So examples of contact forces include friction, air resistance, tension and the normal force, and non-contact forces, forces produced when objects can be physically separated. Examples of non-contact forces include the gravitational force, the electrostatic force, and the magnetic force. So objects can exert non-contact forces by transmitting a field in space. So as we said before, a field is a region of space where a body can experience a force. So for example, the Earth's gravitational field is a region of space where you can experience the Earth's gravitational force, and these are represented by field lines. Now a source is always required to produce a field. For a gravitational field, this is an object with mass, and we can visualize the effect of gravitational field with field lines. Now these are drawn as straight lines from the object with arrows on them indicating their direction. Now any massive object inside a gravitational field will experience a gravitational attractive force the objects do not need to be touching. So we know gravity is a universal attractive force acting between all matter. Now different massive objects can have interacting field lines, but they cannot overlap. So field lines from massive objects can join up but not cross. So here's an example of two gravitational fields interacting. In the centre here, the resultant gravitational field is zero, as the two field lines cancel each other out as they're exerting forces in opposite directions. Now for a gravitational field, the field line should always be pointing towards the massive object. So we say the field lines should show the movement of a test mass in the field if it was placed at this point. Now, any test mass would move towards an object producing the gravitational field, as gravity is always attractive. This leads to another name for a field line, which is a line of force, as it shows the line of action of the force acting. Now, the strength of a field is determined by its field density, which is the number of field lines in a given area. In this field, the smaller the separation with the source, the denser the field lines, and the stronger the non-contact force experienced. This means, in this instance, the smaller the separation between yourself and the surface of the Earth, the stronger the gravitational force experienced by the object. This indicates that as you move away from an object, the gravitational field strength decreases as the field lines spread out. The field lines spread out as a sphere, which has a surface area of 4 pi r squared. Now this happens as we assume the source is a point mass or a symmetrical object. So we know in this case the gravitational field strength decreases as a function of r squared, which is what we call a radial field. Now we note that the field extends all the way to infinity, but it gets weaker as the distance from the centre of mass of the objects increases, eventually becoming negligible at long distances. Now the field is produced from the centre of mass of the massive object producing the field. In most cases this is the geometric centre of the object. It is not the surface of the object. The lines of a gravitational field will only meet at the centre of a test mass or at the centre of mass of a massive object. Now, as you can see in this diagram, the radial fields for a spherical mass and a single point mass are very similar. This means we can model even a large planet or star as a point mass with field lines converging at the centre of mass of the object. Now, the density of the field lines indicates the gravitational field strength. The lower the density of the field lines, the smaller the gravitational field strength. The higher the density of the field lines, the larger the gravitational field strength. So a variation in the gravitational field strength on a surface of a planet is most likely caused by the material varying in density for the same volume. The greater the density of material for the same volume, the greater the mass, the greater the gravitational field produced. So in this instance, under the surface of K, the rocks are denser than under the surface of J. Now, the Earth's gravitational field can be mapped and minute variations can be detected. These local variations may be due to topography, e.g. mountains, craters from meteorite impacts, but also due to the composition of the Earth. Gravimetry is used in mineral prospecting as denser rocks, such as those containing metal ores, cause higher than normal local gravitational fields on the Earth's surface. And the same technique is used to search for oil. Since oil-bearing rocks have a lower density than the surrounding rock, the gravitational field strength above an oil deposit can be slightly lower than in the surrounding area. Now, objects can produce fields of two different shapes. One is called a radial field, the other is a uniform field. The radial field is produced by any particle or point mass, whilst a uniform field is assumed to be the pattern when moving close to a massive object, as it's difficult to observe the curvature. Now, in both instances, the gravitational field lines point in the direction a massive object would take. But in a radial field, the gravitational field strength decreases with distance in the field, but for a uniform field, the gravitational field strength is constant throughout the field. Now, in both cases, the field lines indicate the movement of a massive object placed in the field. So to summarise what we've learnt in today's lesson, gravitational fields are due to objects having mass. Modelling the mass of a spherical object as a point mass at its centre, gravitational field lines are used to map gravitational fields, and the concept of gravitational fields as being one of a number of forms of fields giving rise to a force. Now, if we've been successful and we've learnt in today's lesson, we should be able to define what a gravitational field is, model the gravitational field of a massive spherical point mass, and evaluate different gravitational force diagrams. So thank you so much for watching this lesson on gravitational fields, which is part of the gravitational fields topic in Module 5, the Newtonian World and Astrophysics of OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this video, which is part of Module 5 in OCR A-Level Physics of the Newtonian World and Astrophysics, where we looked at the concept of gravitational fields and the topic of Newton's law of gravitation. So if we've been successful and we've learned in today's lesson, we should be able to calculate the gravitational force of attraction between two objects, describe how gravitational attraction varies with distance, and calculate how gravitational attraction varies with distance. So in this lesson we're going to be looking looking at the following parts of the OCR A-Level Physics specification 5.4.2 Newton's Law of Gravitation. Now, Isaac Newton determined that a gravitational force existed between two massive objects. He deduced that the magnitude of this force F between mass m1 and m2 is proportional to the product of m1 and m2 and inversely proportional to the square of the distance between them. And he also concluded that this force is always attractive. So these three principles form the basis of Newton's law of gravitation. So the relationship between force and separation is F is equal to 1 over r squared. So fundamentally, when the separation is doubled, the force exerted decreased by a factor of 4, 2 squared. Now, both gravitational fields and electrical fields follow the inverse square law when considering the force between two objects. This occurs as both gravitational fields and electrical fields work by the same underlying mechanism. So both field lines spread out as spheres. This gives a 1 over r squared relationship due to the surface area formula of a sphere. So if we think of it as the following, we can see that as we increase our distance from the mass, the larger the spherical gravitational field. So because both the field lines are spread out as spheres, this gives a 1 over r squared relationship due to the surface area formula. So we know the gravitational field lines are spreading out over a greater area. And the area is given by the link to the equation 4 pi r squared, which gives our inverse square relationship. Now, there are two major differences between gravitational fields and electrical fields. The field strength of each field, which is represented by different constants in the equation, and that the electrical field can be attractive or repulsive, which is represented by a plus or a minus. The gravitational field can only ever be attractive. Now, if we go back to the idea of Newton's law of gravitation, you must be able to state the relationships of Newton's law of gravitation as well as state the mathematical equation. So as we said before, our two equations are that the force is proportional to the product of m1 and m2, and the force is also inversely proportional to the square of the distances between them. So you've got to be able to link the separations of the objects with the magnitude of the gravitational force of attraction. So at a distance of 2d apart, the force is F over 4. At a distance 3d apart, the force is F over 9. And at a distance of 4d apart, the force is F over 16. Now we could also now state our equation as Newton's law of gravitation is equal to F, which is equal to F is equal to g m1 m2 over r squared. Now remember, we know this force is always attractive, and it means that the relationship between the force and the separation is F is equal to 1 over r squared, which implies that gravitational fields are radial, which is the case on large scales for any gravitational fields. Now we must note that big G in this equation is the universal gravitational constant, which is equal to 6.67 times 10 to the minus 11 newtons meters squared kilograms to the minus 2. Now to note, this value is very small, which is why gravitational forces can only be easily observed on very massive objects. And again, this constant is much smaller than the electrical field constant, which is why the gravitational force is generally much weaker than the electrical force. Now please remember, in this instance, F indicates the magnitude of the force only. Now the direction of the force is always acting towards the other object, so it is always acting towards the common centre of mass. Now m1 and m2 are the masses of the objects producing the gravitational attraction, where r is the separation between the two massive objects, and we measure this from the centres of masses of the objects. It is not measured from the surfaces of the objects. Now please remember that the force that is produced is the same in magnitude for both masses in the situation. Now this is a consequence of Newton's third law of motion. Now this resultant force will cause the objects to accelerate towards each other. The acceleration experienced by each object may be different as it depends on the mass of the object. So we know A is equal to F over m, which is Newton's second law of motion. So again, finally, for this equation, we assume a few ideas. Assumption 1 is that the masses are point masses, so the objects have a uniform density and that there's a vacuum between the objects. Now in the previous segment we've looked at just the magnitude of the force. Now when we consider the direction of the gravitational force, a minus sign is also required to show that the gravitational force is an attractive force. In Field's notation, a negative force always denotes an attractive force. So to clarify, Isaac Newton measured the gravitational force between two massive objects. This non-contact force is produced as their gravitational fields interact with each other. Both objects experience the same force in this concept. This occurs as both massive objects are inside a gravitational field. Now, both objects will experience the same force and have a resultant force which acts on them, which causes them to accelerate. Now, the size of the acceleration can be calculated by Newton's laws of motion, where acceleration is the resultant force divided by the mass. Now, if several objects are involved, the resultant force of gravitational attraction can be determined by vector addition, as with other force additions. So if the interaction is in one dimension only, then the calculation uses addition and subtraction. So for example, the force on A here is FA plus FAB plus FAC. The force on B is FBC minus FAB. And the force on C is minus FAC minus FBC. Now the same process applies in two dimensions, but in this case we need to use Pythagoras' theorem or the sine or cosine rule if the vectors are not at 90 degrees to determine the resultant force. So for example, in this idea we can look at what the resultant force on B is going to be due to the gravitational attraction between A and B, and then also A and B and also B and C. So we can see that the force on B is equal to the square root of FAB squared plus the square root of FAB squared plus FBC squared. Now here we can look at an example calculation using the laws of gravitation. The distance from the centre of the Sun to the centre of the Earth is 1.5 times 10 to the 11 metres. The mass of the Sun is 2 times 10 to 30 kilograms, and the mass of the Earth is 6 times 10 to 24 kilograms. Calculate the force of gravitational attraction between the Earth and the Sun. So we know F is equal to g m1 m2 over r squared. That's our equation of Newton's law of gravitation. We can then substitute the values in to identify the two masses and the separation between the two centres of mass from the question and place these into the equation. So F is equal to 6.67 times 10 to the minus 11 times by 2 times 10 to the 30 times by 6 times 10 to the 24, all over 1.5 times 10 to the 11 squared. This gives us our value of 3.6 times 10 to 22 newtons. Now please remember this is the force exerted on both objects, and the r term in the equation is squared. People commonly forget to do this in questions. So to summarise what we've looked at in today's lesson, gravity is a universal attractive force acting between all matter. The magnitude of the force between point masses is equal to g m1 m2 over r squared, where g is the gravitational constant. So if we've been successful and we've learnt in today's lesson, we should be able to calculate the gravitational force of attraction between two objects, describe how the gravitational attraction varies with distance, and calculate how the gravitational attraction varies with distance. So thank you for watching this lesson on Newton's law of attraction, which is part of the gravitational fields topic in Module 5 of OCR A-Level Physics, the Newtonian World and Astrophysics. Thank you so much and have a lovely day. Hello and welcome to the following lesson for OCR A-Level Physics in Module 5, the Newtonian World and Astrophysics, in the topic of gravitational fields and on the concept of gravitational field strength. So if we've been successful and we've learnt in today's lesson, we should be able to define what a gravitational field strength is, calculate the gravitational field strength for different gravitational fields, and then finally describe how gravitational field strength varies with distance for different gravitational fields. So we're going to be looking at the following part of the OCR A-Level Physics specification, which is Newton's laws of gravitation. Now we have considered the physics behind the gravitational field. We have also considered the force exerted on massive objects placed inside the field. Now this is calculated with Newton's law of gravitation. However, this value is dependent on the objects in the field. We need to also consider the effect of the gravitational field independent of the objects placed inside of it, and this is the gravitational field strength. Now gravitational field strength can be shown on the gravitational field diagrams as the density of the gravitational field lines. Gravitational field strength is the force per unit mass experienced at a position in the field. Now for radial fields, the gravitational field strength changes at different places of a radial field. Whilst for uniform fields, the gravitational field strength is the same everywhere in a uniform field. Now gravitational field strength is a vector quantity, and we say gravitational field strength is measured for a small test mass placed in a gravitational field. Now the test mass must be small, otherwise it might pull so much on the other object that it changes its position and alters the field. Now, as gravitational field strength is a vector quantity, it always points towards the centre of the object producing the gravitational field. This is shown as the field lines have arrows on them pointing in the direction a mass would move. Now, our units of gravitational field strength are newtons per kilogram. Now, in a uniform field, as we assume the density of the field lines to be constant, we can assume the gravitational field strength to be constant. And this is what we assume at the surface of the Earth, as shown in the following diagram. Now, even at the top of the tallest mountain, the increase in the distance from the centre of mass of the Earth is negligible. So this allows us to use the standard equation to calculate the gravitational field strength, which is G is equal to F over m, where F is the gravitational force experienced by an object in the field. M is the mass of the object experiencing the gravitational force. Now this is the general equation for gravitational field strength of any field. So here's an example question. An 80 kilogram astronaut feels a force of 130 newtons due to the gravity on the moon. What is the value of G on the moon? So the first step is to write out the equation, G equals F over m. The second step is to place the values into the equation, G equals 130 over 80. Our final step, step 3, is to calculate the values. G equals 1.625 newtons per kilogram. But remember to give all values the appropriate number of significant figures with a unit. So it should be 1.63 newtons per kilogram. Now, whilst this is the general equation for the gravitational field strength of any field, it can only calculate the field strength at that point in the field. Now, in addition, the equation indicates that G is a force divided by a mass, so it can also be considered an acceleration, as this is a force divided by a mass also. So this means that another unit for the gravitational field strength is meters per second squared. In other words, the gravitational field strength at a point is the same as the acceleration of freefall of an object at that point. So G is equal to A. Now, an object that falls freely is unsupported. Although the object in this situation is normally described as being weightless, it's better described as unsupported because it's acted upon by the force of gravity alone. Now, in a radial field, as the density of field lines decrease with distance by a factor of 1 over r squared, we must assume that the gravitational field strength does this also. We cannot assume that the gravitational field strength stays constant when you move great distances from or to a massive body. Now, this is reflected in the equation for the gravitational field strength of radial fields. G is equal to big G big M over r squared, and this is derived from looking at Newton's law of gravitation. If F is equal to G big M small m over r squared, and we know G is equal to F over m, we can substitute this into the equation, where we can say G is equal to big G big M m over r squared over m. The small m's will cancel through, so G simplifies to Gm over r squared. Now technically the true equation is G is equal to minus Gm over r squared. This is because it's a vector equation for gravitational field strength. All attractive field quantities are given a minus quantity as you need to place energy into it to remove the object from the field. Now it's easier to work out the magnitude of the gravitational field strength and state it acts towards the centre of mass of the system. So, from our equation, we can see that for a radial field, the gravitational field strength at a point is firstly directly proportional to the mass of the object creating the gravitational field. But it's also inversely proportional to the square of the distance from the centre of mass of the object. This means that when the distance is 2r, the new gravitational field strength is 1 over 4. This means that when the distance is 3r, the new gravitational field strength is g over 9. And this means that when the distance is 4r, the new gravitational field strength is g over 16. So here's another example question. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and its radius is 6.37 times 10 to the 6 meters. Find the value of G at the surface of the Earth. Well, the first step is to write out the equation G equals big G big M over r squared. We place our values in, so G is equal to 6.7 times 10 to the minus 11 times by 5.98 times 10 to the 24 over 6.37 times 10 to the 6 squared. This will calculate out to be G to be 9.8298. but we always give our values to the appropriate number of significant figures in units. So G is equal to 9.83 newtons per kilogram. So to clarify, G equals big G, big M over r squared, where G is the universal gravitational constant, M is the mass of the object creating the gravitational field, and r is the separation between the object in the field and the object making the field. Now the value of G at the surface of the Earth is 9.81 newtons per kilogram. This will decrease as you move off the surface of the Earth by a factor of r squared. And this is another example of the inverse square law in physics. So we know that the gravitational field strength at a point in a field is independent of the mass placed there. It's actually a property of the field. So two objects of different mass placed at the same point in the field will experience the same field strength but will feel different gravitational forces. So here is a gravitational field strength and separation graph for a planet like the Earth. If you were to tunnel through the Earth towards the core, the gravitational field strength would decrease linearly until it reached zero when you're at the centre. Essentially, you would hover in the centre of the Earth if you reached it and it was hollow. Conceptually, this is because all the mass would be pulling you equally in every direction, making our resultant force zero, meaning you wouldn't accelerate in any direction. Now the graph trend is shown with the following. We know the volume of a sphere, like a planet, is V equals 4 over 3 pi r cubed. We know the density of a sphere, like a planet, density is equal to mass over volume. So we can substitute the equations and make m the subject. So m is equal to 4 over 3 pi r cubed times by rho. So therefore we can use the equation for G and get the equation for mass to be the following. So we can say G equals big G m over r squared, so is equal to G over r squared times by 4 over 3 pi r cubed times by rho. We can then simplify to say G is equal to 4 over 3 G pi rho r. So this tells us that within the Earth's surface, i.e. when small r is smaller than big R, the gravitational field strength G is directly proportional to the distance d from the centre of the planet. Now as we mentioned before, gravitational field strength is a vector quantity. This means you can add them up to find the combined effect of more than one object. But remember, you must carefully consider the direction of the field. So for example, you could be asked to find the resultant gravitational field strength at point P. So a model question could say what is the resultant gravitational field strength at point P, where you can see one planet has a mass of m and is a distance of x from P, and the other planet has a distance of 2x from P and a mass of 4m. So the first step is to take one direction as a positive. For example, let's take the right hand side of P to be a positive. We would sum the effect of each sphere, remembering that G is equal to big G big M over r squared. So we can say G is equal to G 4m over 2x squared minus Gm over x squared. We can then work it through, and actually when we work it all out, we can see that G is equal to 0 newtons per kilogram, as the two gravitational field strengths will cancel each other through, and we've given our value to the appropriate number of significant figures in units. So, what we can say is that if we've been successful in today's lesson, we should be able to firstly define what gravitational field strength is, then calculate the gravitational field strength for different gravitational fields, and then finally describe how the gravitational field strength varies with distance for different gravitational fields. So to summarise, gravitational field strength is G is equal to minus Gm over r squared for a point mass. The gravitational field strength is uniform close to the surface of the Earth and numerically equal to the acceleration of freefall. So, thank you so much for watching this lesson, which is part of the Module 5, the Newtonian World and Astrophysics, which is part of the OCR A-Level Physics specification, for the topic of gravitational fields on the concept of gravitational field strength. Thank you so much for listening, and as always, have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics. In Module 5, the Newtonian World and Astrophysics, in the topic of gravitational fields and on the concept of gravitational potential. So if we've been successful and we've learnt in today's lesson, we should be able to define what gravitational potential is and why it is zero at infinity, calculate the gravitational potential for all objects, and understand what equipotential surfaces are and their importance in gravitational fields. So we're going to be looking at the following part of the OCR A-Level Physics specification, 5.4.4, Gravitational Potential and Energy. Now, if we consider a gravitational field produced by a mass, any other massive object placed in the gravitational field will become a store of gravitational potential energy. This gravitational potential energy store is produced because of a resultant gravitational force acting on the object due to being in the gravitational field. So this energy is due to the attraction produced between the masses. Now this gives us the concept of absolute gravitational potential, and this is the gravitational potential energy stored per unit mass due to being placed at a point in the gravitational field. And we give this quantity the symbol V. Now we can set the absolute gravitational potential to be zero at any place, however we choose to set this at infinity, as shown in the following diagram. Now we define infinity as any region outside of the gravitational field. Now we set infinity to have zero absolute potential as the particle or object is outside of the field, so feels no force from the field, and it is no longer a gravitational potential energy store. Now previously we have said that gravitational fields extend out to infinity, so this seems a paradox. However, here by infinity though, we really mean as far away from all masses in the universe as we need to be to make the gravitational forces negligible in whatever context we are looking at. Now all masses attract each other, so it takes energy, that is external work must be done, to move the objects apart. This means that all values of gravitational potential are negative. So we can summarise the concept of gravitational potential as the following: that when an object falls towards a massive object, it will be due to gravitational attraction. Now work would need to be done to pull the object away from that massive object. So the absolute gravitational potential is the energy stored per unit mass in an object due to being placed in the gravitational field. Now we can work it out with the equation V is equal to minus gm over r, where g is the universal gravitational constant, m is the mass of the object producing the gravitational field, and r is the separation between the object in the field and the object making the field. Now this is not the inverse square law. Rather, when the distance doubles, the potential halves. So when the distance trebles, the potential decreases by a third. So we can say that the potential and the separation are inversely proportional. Now gravitational potential is always considered negative on the surface of a mass and increases with distance from the mass. This is because energy needs to be placed into an object to escape a gravitational field, as gravity is always attractive. So, to reach infinity, which we define as zero, we must place a positive value in, so therefore it must start off originally as a negative value. Now gravitational potential is a scalar, as both energy and mass are scalars. Now this makes it one of the only scalars to be given a negative term. Now this equation only works when we consider the mass produced in the gravitational field is a point or a spherical mass. Now please note the minus sign is not optional. All real potentials are negative, and the zero of potential is at infinity, since all objects store no energy gravitationally at infinity. Now the definition of gravitational potential refers to a mass being brought into the field rather than being removed from the field. Now potential, like field strength, is a property of the field at a point and is independent of the object placed there. Two objects with different masses at the same point in the field are subject to the same potential but will have different energies. So, for example, if the gravitational potential is minus 20 megajoules per kilogram, in other words it means it would require 200,000 joules of work to move a unit mass from that point to infinity. Or we could say it would require 40 megajoules of work to move 2 kilograms from that point to infinity. So we can summarise the concept of gravitational potential with the following diagram. Now note, gravitational forces are always attractive. This means that as r decreases, positive work is done by the mass when moving from infinity to that point. When a mass is closer to a planet, its gravitational potential becomes smaller, more negative. Now as the mass moves away from a planet, its gravitational potential becomes larger, less negative, until it reaches zero at infinity. Now as we've said, all values for gravitational potential are negative in a gravitational field. However, changes in gravitational potential can be positive or negative depending on the direction of motion. Now, also, when the distance r becomes very large, the gravitational force tends rapidly towards zero at a point further away from a planet. Now, here's an example question regarding gravitational potential. Find the gravitational potential V at the surface of the Earth. The Earth's mass is 5.98 times 10 to the 24 kilograms, and its radius is 6.37 times 10 to the 6 meters. Our first step is to write out the equation, V equals minus gm over r. The second step is to place the values into the equation. V equals minus 6.67 times 10 to the minus 11 times by 5.98 times 10 to the 24 over 6.37 times 10 to the 6. This gives us a value of minus 6.2616 times 10 to the 7. Remember to give all our values to the appropriate number of significant figures with a unit. So our answer is V is equal to minus 6.26 times 10 to the 7 joules per kilogram. Now, the absolute gravitational potential is the energy stored per unit mass in an object due to it being in the gravitational field, which we can show within relationship-wise with the following graph of V against R. Now, if we know that V is proportional to R, so therefore if R doubles, then V will halve. The potential will tend towards towards zero as R approaches infinity. Now, the potential will tend R towards zero as R approaches infinity, which is an important idea, and the most negative value of V is equal to the radius of the massive object. Now, by using tangents, we can find the gradient of any point of the graph, so our gradient is delta V over delta R, which is called the potential gradient. Now, the potential gradient is another name for gravitational field strength, as gradient is equal to V over R, which is equal to Gm over R, so therefore is equal to Gm over r squared, which is equal to the gravitational field strength. Now, changes in gravitational potential are more complex if a number of masses are involved. Now, since gravitational potential is a scalar quantity, the total gravitational potential at any point is equal to the algebraic sum of the gravitational potentials from each mass at that point. Now, a graph of V against 1 over r will produce a straight line through the origin, with a gradient equal to minus Gm. So we can summarise the graph of V against R as the following. The key features of the graph are that the values for V are all negative. As R increases, V against R follows a minus 1 over R relation, and the gradient of the graph at any point is the value of G at that point, and the graph has a shallow increase as R increases. Now, the concept of gravitational potential allows us to calculate the gravitational potential energy stored in an object in both a uniform and radial field. Now, we know that gravitational potential is equal to the gravitational potential energy stored over mass. So therefore, we can say that the gravitational potential energy stored is gravitational potential times by mass. So it is minus Gm over r times by m. So it gives us our equation of minus Gmm over r. Now, we know that the further you get from an object, the greater the energy stored in the gravitational field, as something must have more work done against gravity to get you there. Thus, when you're infinitely far away, you have high an energy relative to it as possible. Now, we choose arbitrarily to make the value of energies of all bodies at infinity zero. Then, since this is the highest value of energy, all real values of energy stored gravitationally must be negative. Therefore, the minus sign in the equation is not optional. It must always be included, and all values of energy stored in a gravitational field are negative. This is not the case when we come to electrical fields, because they can be repulsive as well as attractive. Now, in our equation, we've written energy here, but not change in energy. Now, by defining a point relative to which all energy is measured, we can now talk about absolute values of energy rather than changes in energy, and this point, which we define, is at infinity. Now, the energy stored in an object follows an inverse proportion law and not the inverse square law. Now, on moving away from an object, there's an increase in gravitational potential, so any object moving this way would gain gravitational potential energy. Now, if an object has no change in gravitational potential, there is no change in gravitational potential energy. Moving towards an object results in a decrease in both gravitational potential and gravitational potential energy. So, if we consider a gravitational field produced by a mass, Any massive object in a gravitational field becomes a store of gravitational potential energy. Now this is considered a scalar quantity, as the gravitational potential energy is stored in the object. Now this can be considered an absolute quantity, as it's not dependent on any other factor except the gravitational field. Now gravitational potential is the work done per unit mass to move an object from infinity to a point in the gravitational field. Now, at infinity, we've defined the gravitational potential to be zero. This is because the object is not in the gravitational field. Inside the gravitational field, the gravitational potential is non-zero, as it's become a gravitational potential energy store due to being in the field. So our absolute gravitational potential is our energy stored per unit mass due to an object being placed in the field. Our gravitational potential is the work done per unit mass to move an object from infinity to a point in the gravitational field. So, if we say that gravitational potential is the work done per unit mass in moving an object into the gravitational field from infinity, this means that the gravitational potential and the absolute gravitational potential will always have the same magnitude. Now this leads to a fundamental concept in physics. Moving an object into different values of potential need work to be carried out. So if we consider a gravitational field produced by a mass, we can see here this is an example of a gravitational potentials found in the Earth's gravitational field. This allows you to understand the concept of gravitational potential in terms of energy stores. So if you let 1 kilogram drop from infinity to the surface of the Earth, it will lose 63 megajoules from its potential energy store. This is ignoring dissipant forces, and the object will have that kinetic energy store when it hits the surface of the planet. So to summarise what we've looked at in today's lesson, gravitational potential at any point is as the work done in bringing the unit mass from infinity to the point, and the gravitational potential is zero at infinity. The gravitational potential is equal to minus gm over r at a distance r from a point mass m, and that leads to changes in gravitational potential. Whilst the gravitational potential energy is equal to mv, which is equal to minus gmm over r at a distance r from a point mass m. So if we've been successful and we've learnt in today's lesson, we should be able to define what gravitational potential energy is and why it is zero at infinity, calculate the gravitational potential for all objects, and understand what equipotential surfaces are and their importance in gravitational fields. So thank you so much for watching this lesson for OCR A-Level Physics. In the Module 5, Newtonian World and Astrophysics, in the concept of gravitational fields, looking at our topic of gravitational potential. Thank you so much for listening, and as always, have a lovely day. Hello, and welcome to this lesson for OCR A-Level Physics in Module 5 Newtonian World and Astrophysics on the topic of gravitational fields, looking at the concept of gravitational potential difference. So if we've been successful and we've learnt in today's lesson, we should be able to define what gravitational potential difference is and why it's important when work is done, calculate the gravitational potential difference for various scenarios, and understand what equipotential surfaces are and their importance in fields. So we're going to be looking at 5.4.4 gravitational potential and energy for OCR A-Level Physics. So if we consider a massive object inside a gravitational field, when a massive object moves in a gravitational field, work can be done. Now this can be calculated by considering the change in gravitational potential in the field. So as you can see here, when an object moves between different potentials, work can be done. Now if we consider the following gravitational field, now the dashed lines in gravitational field diagrams represent the different potentials found in that gravitational field. Now objects can move between different areas of gravitational potential, and this requires work to be done. So we say that the object has moved due to potential difference. Now the potential difference, or delta V, is calculated by working out the difference between the potential areas the object has moved between. So in this example, delta V is equal to minus 240 minus 120, which is equal to minus 120 joules per kilogram. So we can say that the potential difference is the work done per unit mass needed to move an object. This is because the gravitational potential is the energy at each level per unit mass. Now remember that the potential becomes less negative as the object moves away from the object producing the gravitational field. Less work needs to be placed into the object to overcome the gravitational attraction and leave the field to have its potential become zero. Now this works as gravity is always an attractive effect. So this gives our equation of delta V is equal to delta W over m, which we can rearrange to say delta W is equal to m delta V. So this equation tells you the work done needed to move an object between 2 points of different potential in a gravitational field. Or you could say it's the work done needed to move an object over a potential difference in a gravitational field. Now the m term in the equation refers to the mass of the object moving, not the mass of the object producing the field. So as we said before, this equation will tell you that the work done needed to move an object is directly proportional to the potential difference if the mass of the object remains the same. Now we can also write this out as delta W is equal to m delta V is equal to minus gmm over r from using our previous equations. Now when a mass is moved against the force of gravity, work is done. So the work done in moving a mass m is given by the equation delta W equals m delta V, where delta W is the change in work done, m is the mass, and delta V is the change in gravitational potential. This change in work done is equal to the change in gravitational potential energy, and when V is equal to 0, the gravitational potential energy is equal to 0. So the change in gravitational potential energy or work done for a mass of m at a distance r1 from the centre of a larger mass m to a distance of r2 further away can be written as the following, as minus gmm over r2 minus gmm over r1, which can be simplified to be equals to gmm 1 over r1 minus 1 over r2. Now, work is done when an object in a planet's gravitational field moves against the gravitational field lines, i.e. moves away from the planet. Now, moving away from a surface of the Earth, in this example from A to B, there will be an increase in gravitational potential. So we would say any object moving this way will gain gravitational potential energy. In the same diagram, if an object moves from A to C, there is no change in gravitational potential, so there's no change in gravitational potential energy. And in this diagram, moving from B to A results in a decrease in both gravitational potential and gravitational potential energy. So here is an example question regarding gravitational potential difference. A forklift truck does 2120 joules of work to increase a pig's gravitational potential by 26.5 joules per kilogram. What is the mass of the pig? So the first step is to write out the equation. M is equal to delta W over delta V. Placing our value, so 2120 over 26.5. We calculate our value, which is 80, and we give our value to the appropriate significant figures and with a unit, so it's 80 kilograms. Now we can represent the idea of gravitational potential difference with the following graph. And the area under the line for this force against separation graph gives the work done needed to move an object through a gravitational field. So we can link the force separation graph with the changing distance of an object from the centre of mass of an object like a planet. The work done to move a mass up from B to A, i.e. the object gains gravitational potential energy, is shown by the shaded part of the graph. Now the work done can be negative if the object moves or falls from A to B and it loses gravitational potential energy. So as we can see in these diagrams, the dashed lines show the plane of the gravitational field where the gravitational potential is the same. So in this diagram we call these lines of equipotential, and they're like contour lines on a map. So as the potential along the line is always the same or equal, we call it the line of equipotential. Now work is needed to be done to move an object between planes of different potential. There is no change in potential along a line of equipotential. So if an object moved across this equipotential line, no work will be done. So work is needed to be done to move an object between planes of different potential. There is no change in potential along a line of equipotential. So this means a mass can travel along an equipotential line without any energy being transferred. If an object, such as a satellite, moves along an equipotential, its potential energy does not change, as there is no movement in the direction of the force, so no work is done. This is also indicated in the equation delta W equals m delta V. If delta V is 0, delta W is 0. Now in radial fields, the lines of equipotential are spherical spheres. Now the lines of equipotential, as mentioned before, are always represented by dashed lines. Now remember that no work is done when you travel along an equipotential line. A mass can travel along an equipotential without any work being done on the line. Now lines of equipotential are found at 90 degrees or perpendicular to the field lines of the gravitational field, and you would be expected to deduce lines of equipotential from gravitational field line diagrams. Now in our radial field, the equipotential is found as concentric spheres, whilst in a uniform field, the equipotential is found as rectangular planes. Now this diagram here on the screen shows the lines of equipotential in the Earth's gravitational field. Now equipotential surfaces around a spherical mass will also, as indicated before, be spherical. Now this has big implications for any orbiting body in the gravitational field. The potential energy store of a satellite in a circular orbit around the Earth or any orbiting body remains constant, provided that its distance from the centre of the Earth does not change as they're on a plane of equipotential. Now for a satellite in an elliptical orbit, there is an interchange between kinetic energy stores and potential energy stores, as it's not on a plane of equipotential and is therefore changing position. Now moving to a higher orbit increases this gravitational potential energy store as work is done to move away from the Earth. This comes from the kinetic energy store, so the satellite orbits slower. Whilst moving to a lower orbit decreases its gravitational potential energy store as it's closer to the centre of the field. Now this increases the kinetic energy store so the satellite orbits faster. So to summarise, gravitational potential is equal to minus gm over r at a distance of r from a point mass m, and that leads to changes in gravitational potential. Whilst a force distance graph for a point or spherical mass gives you a work done, which is the area under the graph, and the gravitational potential energy is equal to mvg or minus gmm over r at a distance r from a point mass m. So thank you for listening to this lesson. If we've been successful and we've learned in this lesson, we should be able to define what gravitational potential difference is and why it is important when work is done, calculate the gravitational potential for various scenarios, and understand what equipotential surfaces are and their importance in fields. So thank you so much for watching this lesson on gravitational potential difference, which is part of the gravitational fields topic in our Module 5 Newtonian World and Astrophysics for OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics, looking at Module 5 Newtonian World and Astrophysics in the topic of gravitational fields, looking at the concept of planetary motion. So if we've been successful and we've learnt in today's lesson, we should be able to understand Kepler's laws of planetary motion and how to calculate the orbital radius and time period, calculate and understand the escape velocity of an orbiting body, and detail the properties and uses of different types of satellite orbit. So we're going to be looking at the following part of the OCR A-Level Physics specification in this lesson, 5.4.3 Planetary Motion. Now, any object undergoing circular motion will experience a centripetal force. Now, a centripetal force is a name given to the overall resultant force experienced by the object. Now, an object that undergoes circular motion will always have a resultant force towards the centre of the circle. Now, we can consider any orbital motion, such as the Earth orbiting around the Sun. Now, in this orbital motion, the planet will always have a direction of motion tangential to the star. So as we say that as it orbits, the Earth changes direction as it's moving in a circle. So this means that its tangential velocity is changing as its direction is changing. So this means it is accelerating. Now from Newton's second law of motion, we know F equals ma. So if there's an acceleration, there's a resultant force. And not only that, the acceleration and force are directly proportional. Now this resultant force always acts towards the centre of the circle, so the Earth is constantly being dragged towards the centre of the Sun due to this gravitational attraction, so it's a centre-seeking force. So in this situation, the centripetal force causing this orbit is the gravitational force between the Earth and the Sun. Now the centripetal force produces circular motion due to another effect as well. Now an object such as a planet will want to move in a straight line in the same direction, have the same velocity, unless a resultant force acts upon it. This is called inertia. Now this concept was covered previously in mechanics, where we looked at Newton's first law of motion. But the centripetal force always acts towards the centre of the orbit, so the centripetal force is acting perpendicular to the path of the object. Now any force which acts perpendicular to motion will become a centripetal force. Now as the force is acting at right angles to the motion, it cannot affect the speed of the motion. Centripetal forces cannot change the speed of an object. What centripetal forces can do is change the direction of the object. So these centripetal forces cause acceleration by changing the path of the object, not the speed. So centripetal forces cause acceleration by deflection. So the effects of inertia and the centripetal force combine to form the path of circular motion. We can say that the centripetal force provides an acceleration towards the centre of the orbit, whilst inertia prevents the body from falling into the centre. So the centripetal force and inertia combine to ensure that the object follows a circular path. So this means that if the centripetal force was removed, for example the sun disappeared, the object would move in a straight line in the same direction. It would move off in a tangent. So the object would revert back to the laws of linear mechanics. As we can see in the following diagram, we have just summarised what we've looked at in terms of the centripetal force. Now, the equation to calculate the centripetal force is F is equal to mv squared over r. Now in this instance, the centripetal force is the gravitational force, which is equal to gmm over r squared. This means that we can equate the two terms to each other. So we can say mv squared over r is equal to gmm over r squared. When we cancel through terms, we can say v squared is equal to gm over r, or v is equal to the square root of gm over r. We also know that speed is distance over time. Now the distance travelled in one orbit is the circumference of the orbit, which is 2 pi r, and the time taken is the time period. So we can say t is equal to 2 pi r over v. Now we can substitute these two equations into each other. So we can therefore say t is equal to 2 pi r over the square root of gm over r. Now this therefore means we can say that 2 pi r times by the square root of r divided by the square root of gm is equal to t. So therefore we can combine terms together, and what we get is we see t squared is equal to 4 pi squared r cubed over gm. Now we know that 4 pi squared over gm is a constant, so we can then also write this as t squared is proportional to r cubed. Now this is Kepler's third law of planetary motion. Now we can use Kepler's third law of planetary motion to work out the properties of an orbit and body, remembering that Kepler's third law of planetary motion is t squared is proportional to r cubed. Firstly, it shows that the greater the radius of a satellite's orbit, the slower it will travel, the longer its time period will be. So the greater the orbital radius, the longer the time period. And then conversely, the shorter the radius, the faster the time period. Now Kepler's third law of planetary motion also allows for a comparison between orbit and bodies, where we can say t squared over r cubed for one object is equal to t squared over r cubed for another object. But this can only be done if the objects are orbiting the same body. Now in these types of questions you must remember that the time period of the Earth is 1 year, and the radius of the Earth's orbit is given on the equation sheet for your exam. Also remember that as this is a ratio equation, any units can be used for values if they are consistent in the question. For example, you can use years for both time periods for the bodies because it will simplify through as a ratio. Now it's very common in examinations where you're expected to ratio the values of different orbiting bodies. So here's an example question regarding planetary motion. Planet A and Planet B are orbiting the same star. Planet A has an orbital radius of 8 times 10 to the 10 meters and has a period of 18 hours. Planet B has an orbital radius of 1 times 10 to the 12 meters. So calculate the orbital period of Planet B in hours. So the first step is to write out the equation. T squared over r cubed is equal to t squared over r cubed for the two different bodies. We then place the values into the equation. In this instance, 18 squared over 8 times 10 to the 10 cubed is equal to t squared over 1 times 10 to the 12 cubed. We then calculate our values and get t to be equal 795.495. We then give our values the appropriate number of significant figures in units, which is 800 hours. Now we can see in this graphical representation of Kepler's law of planetary motion with orbiting bodies in our solar system. You can see here that the relationship between t and r can be shown using the logarithmic plot. The graph of log t in years against log r in AU for the planets in our solar system is a straight line graph. Now the graph does not go through the origin since it has a negative y-intercept. Now only the log of both t and r will produce a straight line graph. We can also use the full equation of Kepler's third law of planetary motion to work out properties of the body. Now we know t squared is equal to 4 pi squared r cubed over gm. Now this equation can be used to work out the mass of an object at the centre of the system, the orbital radius of a satellite, or the time period of rotation of a satellite. This equation shows that the ratio of t squared to over r cubed is a constant and equal to 4 pi squared over gm. And also shows us that the gradient of a graph of t squared against r cubed must be equal to 4 pi squared over gm. Now in the early years of the 17th century, Kepler published his 3 laws of planetary motion. Now these laws were based purely on observational data for the then known planets. Kepler had no knowledge of gravitational fields. His ideas in fact helped Newton to formulate his own law of gravitation. So Kepler's laws of planetary motion were as follows. The first law is that the orbit of a planet is an ellipse with the sun at one of the 2 foci. Now an ellipse is a squashed or elongated circle with 2 foci, and the orbits of all the planets are elliptical. Now the point in an orbit where the planet is closest to the star is called the perihelion, and the point in an orbit where the planet is the furthest away from a star is called the aphelion. Now in most cases, orbits have a low eccentricity, a measure of how elongated the circle is, so their orbits can be modelled as circles. Now for the Earth, the difference between aphelion and perihelion is only 3%. Now Kepler's second law of planetary motion is that a line segment joining a planet and a star sweep out equal areas during equal intervals of time. So as planets move on their elliptical orbit around a star, their speed is not constant. When a planet is closer to a star, it moves faster. So in this example, between x and y, the planet moves faster than between p and q. Now Kepler's second law states that if the time interval from x to y is the same as this from p to q, e.g. 1 year, the areas A and B must be the same. So this means that if an object moves closer to a star during its orbit, it moves a lot faster and spends a lot less time in that part of its orbit. Now Kepler's third law of planetary motion, as mentioned before, is the square the orbital period t of a planet is directly proportional to the cube of its average distance r from the star. So here we have Kepler's 3 laws of planetary motion. Now Kepler's laws do not just apply to planets or our own solar system. They work for any system where smaller objects orbit around a larger object. This could include moons or satellites orbiting a planet or exoplanets orbiting a star. This is useful because measuring things like time period and orbital radius are commonplace in modern astrophysics. Therefore, useful and interesting data about the mass of orbital systems can be deduced from experimental data. Now we can also consider the energy stores of an orbiting object. All orbiting bodies have 2 energy stores. We say the total energy is equal to the kinetic energy store plus the gravitational potential energy store. Our kinetic energy store is due to movement, and our gravitational potential energy store is due to the position in the field. Now for an orbiting body, the total energy must always stay constant. So if the kinetic energy store increases, the gravitational potential energy store decreases. So when the orbital radius decreases, the orbiting body speeds up. Now, conversely, if the kinetic energy store decreases, well, therefore our gravitational potential energy store decreases. So when the orbital radius increases, the orbiting body slows. Now, for a circular orbit, the orbital radius is constant, so the speed of the orbit is therefore constant. Now, we can work out the kinetic energy store as is equal to a half mv squared, and our gravitational potential energy store is equal to minus gmm over r. Now remember, we must use GPE is equal to minus gmm over r and not equal to mg delta h, because as this is a radial field, g changes. Now if an orbiting body changes radius, we therefore say that the change in kinetic energy is equal to the change in gravitational potential energy, or a half mv squared is equal to gmm over r. So this allows you to work out the new velocity of the body or the new orbital radius of the body. So we can summarise the energy in orbital bodies with the following. When a satellite is closer to the planet, at the smaller r, there's a lower gravitational potential energy, a higher kinetic energy, and therefore a shorter time period to travel faster. And a satellite which is further away, we can say that at orbit y, where the radius of r is larger, the satellite has a smaller gravitational force acting on it, a smaller speed, a lower kinetic energy, a higher gravitational potential energy, and a longer orbital time period t. So if we go back to our equation of saying the total energy is equal to a half mv squared minus gmm over r, we can therefore say that the kinetic energy of the satellite is equal to a half mv squared, which is also equal to a half m gm over r. Now, this therefore tells us we could also write it out as gmm over 2r. So we can change that in our equation as shown. Now, therefore, we can state that our total energy is equal to minus gmm over r, the gravitational potential energy store, plus gmm over 2r, the kinetic energy store. So when we equate that through, our total energy of an orbiting body is minus gmm over 2r. So when we consider our three different energy stores for an orbiting body, you note that straight away all three energies have a 1 over r relationship, and that the total energy is always a negative, which is important because it's inside the gravitational field. Now, to escape the gravitational field of a mass like a planet, an object must be supplied with an energy equal to the gain in gravitational potential energy needed to lift it out of the field. So our escape velocity is the minimum speed an unpowered object needs to leave the gravitational field of an object and not fall back into the field. Now, we assume that if an object escapes the field, it's at infinity. So therefore, the gravitational potential energy of the object will therefore be 0. Now, whilst in the gravitational field, the gravitational potential energy of the object is a negative. So therefore, to reach infinity 0, a kinetic energy needs to be given to the object. So our increase in gravitational potential energy from a negative to 0 comes from the kinetic energy decrease in the object. So therefore, we can say that our increase in our gravitational potential energy comes from a kinetic energy loss. So a half mv squared is equal to minus gmm over r. So what we can therefore deduce is that we're assuming firstly that only the minimum kinetic energy is needed to escape the field. There's no excess energy left after escaping the field. So we are assuming that there's no dissipative forces acting on our object. So we can therefore rearrange this to work out V and say V is equal to the square root of 2gm over r, which we state is the escape velocity of our gravitational field. Now, it's important to note a few key things. Our escape velocity only depends on the object producing the gravitational field and the distance from the centre of the field, not the object in the field. Now, remember, r is the distance from the centre of the field, not the surface that the planet, of the planet or the object that it is on. Now, also remember that this value is an idealized value for escape velocity. In reality, it will be a lot higher than the calculated value, as not all energy is change store at the start of the journey, and there will be dissipative forces present. Now, therefore, the escape velocity will always have a higher value than the orbital velocity of an object in the field. Otherwise, the object wouldn't be able to actually orbit. Now, the composition of the atmosphere on different planets depends on several factors, including the average temperature of the planet and its surface gravitational field strength. If the temperature is high enough, atoms or molecules in gases will reach the escape velocity and leave the gravitational field of the planet, drifting off into space. Now, in order to escape the gravitational field of a planet, an individual atom or molecule from a gas must have a minimum speed of V is equal to the square root of 2gm over r. Now, the average kinetic energy of a single gas atom or molecule is given by the equation of half mc squared, where c RMS, the root mean square speed of the molecules, or is also equal to 3 over 2 kT. So this tells us that at any given temperature, some molecules will always be travelling faster than the RMS speed. So therefore it tells us that there will be molecules travelling faster than greater than the square root of 2gm over r, and therefore escape, and this will actually remove the atmosphere from that planet or satellite. So here's an example question regarding escape velocity. Calculate the escape velocity of the Earth. Now the first step is to write out the equation. V is equal to the square root of 2gm over r. We then place our values into the equation. So V is equal to the square root of 2 times by 6.67 times 10 to the minus 11 times by 5.98 times 10 to the 24 over 6.37 times 10 to the 6. We then calculate it to be 1.1190 times 10 to the 6. We therefore give our values to the appropriate numbers, so we get our answer to be 1.12 times 10 to the 4 meters per second. Now, there are several different possible stable orbits. The first one is a synchronous orbit, where the orbiting object has an orbital period equal to the rotational period of the object it is rotating. When this is for the Earth, this is called a geostationary orbit. A geostationary orbit has an orbital period of 24 hours. Now, to achieve this, the orbit of the object must be in the plane of the equator. So this means the object will always be directly above the equator. So we say that the object will be in the same position on the Earth, so therefore it will orbit in the equatorial plane. It's an equatorial orbit. Now, as mentioned before, a geostationary orbit will have an orbital period of 24 hours. It'll always be in the equatorial plane, so it'll have an orbital radius of 42,000 kilometers, which is 36,000 kilometers above the surface of the Earth. Now we say, therefore, the satellite moves in the same direction that the Earth rotates. Now, also, these synchronous orbits, we would use these orbits for communication satellites. This is because the satellite stays fixed in comparison to the surface of the Earth, so signals can be easily sent to them. We also have low orbiting satellites, which is a satellite which are between 180 and 2,000 kilometers above the surface of the Earth. These satellites in these orbits are cheaper to launch as they don't move as much on takeoff, and they receive less powerful transmission signals as they are closer. So this makes the satellites useful for communication, weather and monitoring sites. However, these satellites are very close to the surface of the Earth and orbit at a faster period than the Earth rotates. So this means an individual satellite would not cover all of the Earth. So multiple satellites would need to work together in a network to achieve constant coverage. Or what we would say is that an individual satellite could be used to map the entire surface of the Earth over a much longer period. Now, weather and mapping satellites have what we call a polar orbit, going from north to south pole and vice versa. This allows them to scan multiple parts of the Earth over a period. Now, this type of orbit offers a complete view of the Earth over a given period, as the Earth will rotate beneath the path of the satellite, ensuring the satellite covers all parts of the globe after a number of orbits, so it's useful for mapping and reconnaissance. So here's a diagram showing the different stable orbits: the polar orbit, the low Earth orbit, and finally the equatorial or geostationary orbit. So to summarise what we've looked at in today's lesson, we've looked at Kepler's 3 laws of planetary motion. The fact that the centripetal force on a planet is provided by the gravitational force between it and the Sun. The equation is t squared is equal to 4 pi squared over gm times by r cubed. So our relationship with Kepler's third law is t squared is proportional to r cubed, which is applied to systems other than our own solar system. We know the idea of geostationary orbits and use of geostationary satellites, and are finally the concept of escape velocity. So if we've been successful and we've learnt in today's lesson, we should be able to understand Kepler's laws of planetary motion and how to calculate the orbital radius and time period, calculate and understand the escape velocity of an orbiting body, and then detail the properties and uses of the different types of satellite orbit. So thank you so much for listening and watching this lesson, which is part of Module 5 Newtonian World and Astrophysics for OCR A-Level Physics, on the concept of gravitational fields, looking at the topic of planetary motion. So thank you so much, and as always, have a lovely day.